Swayam Prabha. Digital India. Educated India.
Hello everyone and welcome to the new discussion of this Geographic Information Systems course. And today we are going to discuss how to assess quality of a DEM. This I have been telling earlier in earlier discussions that one day we will discuss about the how assessing the quality of a DEM. Why it is necessary? Because nowadays there are various options to generate digital elevation models, and various digital elevation models from generated using different remote sensing techniques or survey topo sheets have been made available on internet. Most of them are free of a moderate resolution DMs, and therefore whenever we employ either a interpolation technique for our own surface or for using already available digital elevation models, then we must try to assess the quality of a DEM. And this should start with first with the metadata. If you have downloaded a digital elevation model from an internet source, and then the best thing is first to study the metadata. Also should know how it has been generated, which remote sensing or otherwise a technique has been employed, and what are the things which are may matter in future while in terms of accuracy. So in this as you know that whenever we go for these kind of generations, which is surface generation or in form of DEM, because it is not possible to visit each and every point on surface of the earth or part of the earth, and therefore some technique has to be employed which also involves your interpolation. And then as you know that when we have developed a spatial database on a GIS platform, and we start analyzing things, ultimately we may go up to depending on our requirements spatial modeling or for prediction, and that reliability of that prediction or modeling will definitely depend on the quality of source data, how good quality the data is, and questions are generally asked that what is the accuracy of your prediction. So let me give you one example that a few years back I was hearing a presentation by a person on landslide hazard zonation mapping, and in that landslide hazard zonation mapping a question was asked to him that what is the accuracy or how good your prediction is, and he had to say that it is 50%. And 50% prediction is virtually no prediction at all, because anybody can predict that there may be rain today or may not be rain today. So that does not mean anything in terms of prediction. And so whenever we go for spatial modeling employing digital elevation models, and one of the major sources of information is our digital elevation models, and therefore we must assess the quality. One, inherent errors, because there can be various types of errors. So first we have to assess the inherent errors, and there might errors during processing. So processing errors might be in our hands to check and rectify, but if there are errors which are inherent, the organization which has generated that digital elevation model or collected data in the field, and then later on I have generated digital elevation model using that data set, then I would call as a inherent error, or things which are lacking in that one. So, we must know, and this you can always know if you are downloading that any DEM, whether it is SRTM or ESTER-DM or CARTOSAT, if you go through the meta file and also how it has been generated, some documents must be available, then you will get an idea about the inherent errors. So, this is very important part. Before you imply any data, you must know the limitations, you must know the errors also. Now, as you know that DEM is a storehouse of information. That means that we can drive various informations, various surfaces, various trends using digital elevation model. And these derivatives are very sensitive to quality of the DEM. So, if the quality of the DEM is poor, you can guess that what is going to be the results when I drive some data. For example, if a digital elevation model is having lot of errors, and if I generate a slope map or aspect map, then I cannot say with high level of confidence that my derivative using that particular DEM is very good or accurate. So, that is why this inherent errors really matters a lot, and therefore, generally you would find that many times people will just download the DEM and will never bothered about inherent errors. And this knowledge or the lack of this knowledge about the errors in a DEM still is not discussed much, neither on literature or in practice. People do not really bother, but that will make a huge difference in the confidence level of in your results. So, one definitely spend some time to assess the quality of a DEM. How you can assess? There are various ways one can assess, like errors in DEM can be very large when you are having shaded slopes. Also, because why on shaded slopes? Because if even if I am using stereo pairs or I am using INSAR based DEM, then in a hilly terrain, these shaded slopes where the illumination is not reaching, or because of orientation of that particular slope or valley may hinder data, and that ultimately may get reflected in terms of errors in a digital elevation model, and therefore, one has to be really careful about that. Sometimes when digital elevation models are generated for very flat areas, smooth terrain, featureless terrain, again there might be lot of errors. For example, if I am working in a desert area and there are not even dunes, then it becomes really very difficult, and that digital elevation model, no matter whatever the technique which has been employed, may also generate lot of errors. Similarly, if an area is fully covered with snow like in Antarctica or in north polar regions, then you may have a lot of problems in a digital elevation model. Now, this is another very important point, that the errors in a digital elevation model are spatially variable. It means that at some location the error may be different, at some location within the same file, within the same surface, that might be different. So, this is because of, as we have discussed about the shaded slopes. So, in some parts which do not have those shaded slopes, the errors may be less, but in the areas where you are having shaded slopes, error may be large. So, it is errors are spatially variable and spatially autocorrelated also. So, in that way it gives a problem about the errors in digital elevation model, and all these errors which we have discussed so far or discussing are inherent errors, because we do not have much control except knowing them, and if possible, if we can avoid a particular digital elevation model, if it is having too much errors, then it is there, but it is very difficult to correct those digital elevation model unless we ourselves are generating digital elevation. Now, while assessing the quality of a digital elevation model, one term we must also discuss here is about the uncertainty. So, they basically as you know, the DEM is a model and say approximation of reality or abstract form of reality. And reality here is the terrain. So, what we are having? We are having a model of the terrain in an abstract form, not in a one-to-one scale. And therefore, this DEM as a model of the real world features or phenomena, which is what present in abstract form, reduced scale. And as you know that in spatial modeling, it is what we try, and that we try to produce whatever results which are approximation or close approximation of reality. And the reality, of course, you can never, the real world you can never generate on the computer or through some modeling, because modeling itself is a representation of that, in our case like in current discussion, representation of the terrain. So, it is not truly a terrain, but it is a representation. Now, whatever is the goal where we are going to use digital elevation model, there may be lack of knowledge about how good a representation of reality is required. So, if we know what are my targets of a project, how accurate the results I have to produce, how reliable I have to produce, and there that can guide us to choose an appropriate digital elevation model, and not only that, but more accurate digital elevation model. So, further is that how well a model represents reality. If it is having errors, definitely it is not going to represent the reality in a good terms, and how reliable the conclusions are. And of course, this reliability or level of confidence will depend how that model has been generated, what are the errors or extent of errors, and whether they are just one error within one file or spatially varying errors are there. If it is there, then things may become complicated. So, this lack of knowledge about a model or about a digital elevation model in our case is can be expressed as uncertainty, and this uncertainty has basically two components. One is the uncertainty about the quality of the data, which is what we are discussing here, and uncertainty about the quality of processing applied to the data. So, you know, this probably to some extent we can control, because this is in our hands. I have got a DEM, now I am processing it, I am driving lot of products out of that DEM. So, there I can have a check. But if I am using ready-made DEMs, available DEMs on internet, then I do not have much knowledge about the accuracy or errors of that DEM. So, our effort should be to learn those inherent errors of any data which I am going to employ for my study. So, the data quality, as you know, is fundamentally dependent on the degree of error within a data set. If errors are very minimum, that means they are the data in case of a digital elevation model is representing through a good representation of a terrain. But if it is the degree of error is very high, then you can think that what reliability you would have and how big uncertainty would be there. As you know also that error is basically a difference between the data set value and the true value. Now, problem here is in many cases we do not know the true value at each location, because a DEM is a continuous surface. That means for each cell I do not know the true value. If I would have known, then definitely I can create a much more highly accurate and high quality digital elevation model. Since those values were not there for each cell, that is why either I have resorted to some remote sensing technique or interpolation technique. So, only we can find the errors where we are having some values, some control points, some spot heights which we consider as reliable heights, or the data may nowadays that data about few points randomly distributed within my study area can come also through differential GNSS. So that way I can get some true values and then can compare and do some statistical analysis and can tell that how good my input DEM is. And as you also know, this we have discussed the two things about accuracy and precision in previous lectures, that accuracy is basically a measure that aggregates or summarizes the errors within a data set. So, sometimes we loosely use, but this because you know the precision depends on the instrument which I am going to use it, but accuracy is basically a statistical term, how close I am to the real value or true value. Now, how this error can be represented. So, a normal way or conventional way of using this root mean square errors or RMSE values. This is how we because there are some way to check it how closely that is. So, we get through this RMSE. Now, variations in error is not communicated by single RMSE value. So, if you are having for one entire data set just one single RMSE value, that may not be sufficient in sense, because as we have learned that errors may vary spatially within a data set, and that is why a single RMSE value will give you some idea about the errors, inherent errors in the data set, but may not be sufficient. So, RMSE, as you know, is based on the difference between the DEM elevation and the elevation of test points or true values measured by field surveys or from an existing source map or other methods. So, if I am having that data, generally if you start trying to assess the quality of a digital elevation model, I am sure from one way or another you may get some test points, some true values for your area which you can employ to assess the quality of a DEM. These are basically RMSE or any other analysis which you would do are basically statistical based analysis. For example, visual examination of the surface model, because if surface model or DEM is suffering from voids, then visually you can also assess. If it is having seams, visually you can assess very easily. But when you involve the statistics, then it can be summarizing by key morphometric characteristics of a DEM can provide valuable additional information about quality of a DEM. That means before even employing a digital elevation model for my own work or analysis, I would require to do some analysis like morphometric analysis over a targeted DEM to assess the quality. So, this is another way of assessing the quality, and therefore, we can hypothesize that the distribution and scale of errors within a DEM are at least partly related to morphometric characteristics of the terrain. Because you know, when you are having a digital elevation model of a highly rugged terrain, then scenario can be very different. However, if you employ this morphometric analysis, you may get that idea about the errors which are inherent in that particular digital elevation model. So, this an accuracy surface would give a better representation of the distribution of error within a DEM than a single RMS error, because of our errors are spatially varying, and therefore, a single RMS error is not sufficient. We need a surface which will tell us where the errors are more, where the errors are less. Very quickly I will go through the sources of DEMs which are available to us, and we will also see that what are the errors associated with this. As you know, we have already discussed these things earlier. So, very quickly I will go that already available DEMs may be USGS DEMs which has been generated from toposheets, SRTM which is based on INSAR remote sensing technology, or self made DEMs also. So, from contours or point interpolation that we do. So, if we are employing a ready made DEM, then the best thing which we have developed in few years time, best technique rather I would say, is to get some elevation points, reference points, test points from some other source that may be independent source. What I mean is maybe from spot heights from Survey of India topo sheets, or maybe from differential GNSS or GPS. Now here I would like to mention that organizations like Survey of India and National Remote Sensing Agency NRSA, they are having a big library of these control points. They call as ground control point, and we discussed these ground control points when we have been discussing georeferencing. So there are, like NRSA has developed a library which is having about 30,000 ground control points of every part of India, and these ground control points, GCPs, are evenly distributed over India. But unfortunately it is that data set or that library is not open to us. But I know that in order to assess the quality of a digital elevation model which has been generated using Cartoset, and it is available at 30 meter resolution freely for India, which you can download from Bhuvan portal. While assessing the quality, they have used those 30,000 ground control points to assess the quality. So in that way, these few test elevation points have been used to assess the quality. How it can be done, which we have also developed, that if it is self-made digital elevation model, then things are little easier in sense, because in every process we are involved. So on errors we can check at every step, keep checking the errors. If found, we go back and do the corrections and then go forward. So if it is self-made DM, then before using all points, whatever the observations you are having for interpolations, remove some random points from the source data. And I will give you an example, like I am having 100 points, elevation points or spot heights to generate a digital elevation model through interpolation technique. So what I mean is that I will remove some randomly some points from those 100 points, and then keep those points for as a separate file, and I will do the interpolation using those 90 points or 90% of points. So let us talk in terms of percentage. So then those remaining 10% points which we kept as a without disturbing them and collected randomly, which can be done very easily on a GIS platform, then I will use those 10% point to check the accuracy of a DM, because those points have never been used to while interpolation was being done. Then I can employ different interpolation techniques and various variants of each interpolation techniques. So that means I can in first hand, what I have to do, if there are 100% points, I will take randomly select 10% points, take out from that, and with 90% points I would do interpolations and generate surfaces using different interpolation techniques, maybe even 10 surfaces, 10 different surfaces employing different techniques. And then I will use those 10% point to check to see that which is showing the maximum variation, which surface is showing maximum variation with those 10% points, because those 10% points have not been used in my interpolation. Now whichever the surface which qualifies for the closest or with minimum variations with test points and the interpolated surface points, then that means now I know that which interpolation techniques I have to employ. And then what I will do, I will use all 100% points and that particular interpolation technique to generate a digital elevation model. So I would know that digital elevation model is better, more accurate than any other interpolation technique. So, this answer will come from the error which I have just discussed about this. Now, those who are interested to learn about how to assess quality of a digital elevation model in much more details, then we are having these two publications in which we have extensively described that how to assess the quality of a DEM. Here is the SRTM and DEM characteristics for two Himalayan region. So, we have one is for very rugged region, one is for less rugged region, and again there is a comparison of Cartosat, DEM and other things. So, there also we have assessed the quality of a digital elevation model. Visually you can do it, I have already told. If there are voids, you can check very easily. If there are seams, you can check very easily. So, there are various ways. Now, there another way is epsilon bends around contour lines and catchment boundaries, like generation of these epsilon bends are polygons basically or buffers drawn around lines to represent the uncertainty in a line position. And there might be some other techniques like Monte Carlo based on stochastic technique, which basically is simulation to drive a sample of potentially valid model outputs reflecting the influence of uncertainty on the modeling process. So, this Monte Carlo simulation is a basically computerized mathematical technique very common to generate random samples data based on the some known distribution for numerical experiments. Now, random generators are there or random selectors are there in standard GIS softwares like in ArcGIS, which you can employ and can instruct the software that I want to select 10% points. So, it will select. Now, you extract those 10% point, keep as a separate file and later on to check, and then finally with 100% point you can generate a surface. So, quality of a DEM can be assessed using ground control points or point heights. This is what we have discussed. Now, further in this one there are various areas which we covered in this one, in this particular example, and digital elevation models were checked using ground control points or spot heights and digitized or brought from digital these survey topo sheets, and assuming that they are providing ground verified elevation values. So, once we employed for 3 different types of terrain, highly rugged terrain and then moderately rugged terrain on the plain area, you can definitely find out that which digital elevation model is good. Though you do not have to do extensive experiment, what you can do in order to optimize this, just use the digital elevation model of your area of interest and different digital elevation models and employ these ground heights, spot heights, or if you are having access to that GCP library, and then check that which elevation model is more close and or having less variations against those test points, and whichever the digital elevation model which is showing the minimum variations is more reliable in that sense. So, spot heights or these spot heights which are available on survey topo sheets which we have derived top to bottom along with. So, the Kanchenjunga area, the top one, then this is a less undulated area, the middle part of Bundelkhand region, and the lower one is just flat part of Indo-Gangetic plain, that is around Roorkee. And this is what we found that there are 3 digital elevation models we employed. So, Aster DEM was on the left side, and then Cartosat DEM in the middle, and then SRTM, all are having 30 meter spatial resolution. Now, this is the library which I was mentioning about the ground control points library GCP, and this is available. This is, I am sorry, this is not available to public. but some details are available about this library. However, as I have already mentioned, there is these 30,000 ground control points which are spread all over the India except for some parts of J&K have been used to validate or to find out the errors in Cartoset DEM which has been generated by the same organization NRSA. Of course, it would have been much better if some independent people would have checked rather than the same organization which generated digital elevation model and ground control points are checking. But nonetheless, we believe that they have done the justice to this checking, and with whatever the errors were there, they must have got rid of those to the maximum extent, and that is why if you go for Bhuvan portal, you would find that there are different versions. So, first they had version 1, then version 2, and currently they are having version 3. So, assuming that version 3 is more accurate than obviously version 1. So, likewise one can really find out the errors. This is what they said when they have used the Cartoset and DEM and see the difference in elevation. If I talk about the Cartoset DEM generated by NRSA, so obviously in hilly regions the error is much larger, but in flat areas, as you can see, that most of these colors are falling in this category. And so wherever undulations are there, remember one point which I discussed about the shadow regions. So in hilly regions you might having problem. So same in the northeast India or in the western Himalayan region, including in Uttarakhand, the error part is much more. Same in the Kutch region where you are also having some undulated terrain, also on the eastern Ghats and western Ghats region also, and some in the central India and Narmada zone area. So there those areas had the large errors compared to flat areas in that particular model Cartoset DEM, and validated or checked using those GCPs. There are some other checks based on using the Ester DEM and Cartoset DEM and driving the drainage network, that means through surface hydrologic modeling, and again you can see that how things are varying, and these one like when they drived there are counts difference are there in because the sources of two digital elevation models are different. Only one thing which is common between Cartoset DEM and Ester DEM is because both are based on stereo pairs and employing photogrammetric technique. So therefore this comparison is in that sense is more valid because the same technique has been used, though sensors are different, but the resolution wise they are same. So the variation which you can see in different drainage lengths is definitely much different in both these models. This part I have already discussed how to assess the visual. So very quickly I will go that this is a digital elevation model generated using survey topo sheets at 1 kilometer resolution, and this is the digital elevation model at 90 meter resolution, but with voids. As you can see, they are marked as a no data value, and then you can make void free as well. However, visually when you zoom it, you may find the seam or you may find some areas which are not as sharp within a digital elevation model, because those have been voids and those have been filled with low spatial resolution and DEM below. Similarly, like SRTM void, this is non-void filled scenario where you are seeing the voids, and in high elevated regions there the voids problem was much there in case of Himalaya. This is also in case of Mount Rainier and Mount Adams which are near Washington and Washington DC USA, and this is what the void free or void filled digital elevation model is. Similarly, a lot of such work is being carried out to assess the quality of different elevation models, employing almost the same technique, that you have to have something true values, or you have to assume some values, true values which are independently collected, and then you compare with the values which have come through a digital elevation model against each cell. So, against those corresponding test points, you get that value and you assess that one. And similarly, here for SAR interferometry, again the GCPs are used, and different residuals have been assessed. This is so Cartosat DM, this is again Cartosat DM at 30 meter, this is 90 meter. So, what you can find that at 30 meter at some different locations, the error is much bigger than in 90 meter. Similarly, also at another location. So, generally as you go higher and higher spatial resolution, the error may become larger. It depends on the terrain basically and the technique which has been employed to generate a digital elevation model. Same thing here. So, the Cartosat, this analysis has been done, and as you can see, this is not highly rugged like Himalaya, but this is Alwar region in Rajasthan. A visible image is there, and then you are having a digital elevation model, and so checkpoints which are shown here as yellow colors or your test points, and when you go through, this is how the number of IC or GCPs or ICPs are there, and you can keep checking the errors in meters. So, various ways one can represent how errors are varying in a digital elevation model, and of course RMSE will give you overall picture, but not the spatially varying errors present in a digital elevation model. So, finally, we come to end of this discussion, the important point which we have to carry, and that is we have to differentiate between inherent errors and also errors generated through our processing. We may not have much control over inherent errors, but the knowledge is very much required, because our reliability of results or level of confidence will definitely depend on inherent errors. Second type of errors, the processing errors, we have to be, which is in our hands, and at every stage we can keep checking, keep finding the errors if at all, and if they are there, correct immediately, then move forward. So, with this I end this discussion. Thank you very much.